So today I'm going to talk about one of my recent work collaborated with Camilla and Antonio and Daniele. And then we just submitted this paper, and then I'm very happy to discuss what we studied here. So let's start. So my talk consists of 7 chapters. So first of all, I will try to explain some introduction, and then next we will talk about some mass generation mechanism in chapter 2, and then we will discuss some the scalar potential constraints as well as the flavor and the perturbativity constraints. And then I will discuss some the numerical analysis and the benchmark scenarios, and then some kind of the new physics searches there. So like vector like quark, lepton, and the MP scalars, all of them. And then I will conclude our findings. So let's start. So first of all, the main motivations for this work was, so first of all, to explain muon G mass of 5.1 sigma based on the data-driven standard model muon G mass determination. Recently, there was a very significant controversy between the discrepancy for the muon G mass, especially if we trust the hadronic vacuum polarization, the determination. Actually, it's very likely that the muon G mass is shrink to about 1.5 sigma or something like that. But in our work, we still trust this 5.1 sigma, and then just consider that part. And then next, we want to determine the secant anomaly while respecting all the standard model constraints. These two are the main motivations. And then lastly, also, unfortunately, we also noticed that there are many inconsistencies in our previous work. Actually, this work was already done in my second paper with Antonio and Steve. However, we noticed that there are many problems in this work, and then so I think we thought this is better to revise this work from scratch. So these three are our main motivations for this work. And then to this end, the model understudy is extended by a full family of vector-like fermions, as well as a standard model like doublet scalar and a singlet flavor. So featuring the type 2 Higgs doublet model and the muon prime global symmetry. And so one of the most important features of this BSM model is to induce the standard model Yukawa interactions. So by mixing with vector-like fermions, which means the new particles are strongly constrained by the standard model parameters. Therefore, in this setup, the standard model Yukawa interactions at the flavor basis are forbidden by the muon prime global symmetry. And the scheme for this work was, so in section 2, we discussed the mass matrix for the standard model fermions with the hierarchy of masses and the secant mixing matrix. And then this feature will be investigated using the scalar and spin, the high energy physics tools. And then in section 3, we discussed the scalar potential constraints with the CP even, order, and charge scalar mass matrix in the alignment limit. And then also the bounded from below limit conditions as well as vacuum stability. And then this investigation will be done via the herbaceous to check the global minimum of the scalar potential, and then Higgs tools to check the exclusion limit of MP scalars. And then in section 4, the flavor physics constraints are confirmed with the muon G mass, our main target. And then our prediction should respect this lepton flavor violating decays upper limits, especially the most significant ones are the tau to mu gamma as well as tau to 3 mu. So especially the tau to mu gamma. And then finally the secant anomaly. And then this investigation will be done via the med graph to check the collider signal as well as the spin to have the branching ratios of new physics particles. Then in section 5, the perturbative constraints are investigated by the normalization group equations. So our benchmark scenarios also must respect this IG runnings. So this is all the constraints we considered in this work. And then in section 6, the PP scenarios will be discussed, in which we also investigated the vector like quarks, leptons, and MP scalars. And then we will conclude this main findings. So now I will talk about the generation of fermion message and mixing. So here the model under consideration is extended by a full family of vector-like fermions, as mentioned, and then one the doublet scalars and the one singlet flavon, and then muon prime global symmetry. So the here uncolored part are the standard model parts at the whereas the colored part are the all new physics particles or the extended gauge symmetry. So here the renormalizable Yukawa interactions can be written like this way. So generally this renormalizable Yukawa interactions are the TV scales, and then after this the singlet flavon phi develops its bevel, then it gives the effective standard model Yukawa interaction. That is our approach. So as you can see, this upper left 3 times 3 plus is standard model interactions, and then while mixing with this heavy fields, actually we are inducing the standard model Yukawa interactions. So this is part of the mass matrix for the charged standard model fermions. We also considered this 7 times 7 neutrino mass matrix, but I just brought the charged mass matrix. So if you are curious, then you can refer to our papers. They are we put all the standard model fermion mass matrices. So after diagonalization, we assign the second and the third standard model generations their masses. So but maybe you can complain that why our first generations remain massless. But this picture can be complemented by introducing one more vector like fermions. However, at the same time, we cannot avoid introducing so many pre-parameters, which we want to avoid definitely. So this is we will say this is the most economical version, but still our model can fit the first generation message. So this is not that we cannot give the message to the first generation, but it can be approximated because they are light enough. So that's what we approach in this model. So this is the most economical version of this data. So actually our model is also strongly inspired by the hierarchical structure of the standard model fermions. So after you integrate out these heavy fields, actually it gives these times 3 times 3 Yukawa mass matrices. So this third generation gives more more significant contribution from the other fermions, and then this is this 2 by 2 gives the second and third generation message. So this is that is the reason why our model respects the hierarchical structure of the standard model. And then lastly, this structure is this zeros can be given by rotating all the three left fields. So this is can be achieved without loss of generality. So this is a very general feature of our model. There is I emphasize there is no any assumption or approximation to get to these features. In this setup, we consider all the scalars develop their pairs as follows. So this is up-type pair, this is down-type pair, and this is singlet pair. And since this model features type 2 Twix doublet model, the scale of the up-type pair and the plus scale of the down-type pair should respect this condition, and then tangent vector is defined by the ratio between up-type pair and down-type pair. Then the second and the third fermions can be parameterized in terms of the Lagrangian parameters. So we can explain this Huchan method and the Huchan method. And if you divide this Huchan method by the Huchan method, actually you get to have these conditions. Here, you can see something interesting, because if tangent beta is larger than 10, then maybe in this case, this up-type Yukawa is the order of up-type Yukawa is quite similar to that of this down-type Yukawa. Whereas maybe you can also consider the possibility where this tangent beta is very low, like let's say 2 or 3. In this case, this Yukawa must respect the large hierarchy between these two parameters. So I will talk about I will discuss this picture later, but in our benchmark scenarios, we get to have this tangent beta is about 10. So generally, our order of the up-type pair is quite the same as the down-type pairs, down-type Yukawas. So the secant mixing matrix in this model features like this way. So this zero comes from the interaction between the singlet vector-like fermions. So by this mixing matrix, we can easily explain the secant anomaly. And then this is the parameterized secant mixing matrix in our model, where this is the ratio between each Yukawas and some other parameters. So and then this parameterization can be reparameterized by the Wolfenstein parameterization. And then by doing so, what we found is actually our model cannot beat all the secant anomalies, like especially this the 3-1 part. This element gives us some logic contribution, which means in this economical setup, even though we cannot fully beat the secant mixed matrix, but as I told you, this picture can be complemented by the introducing one more vectorized fermions. So here from this derivation, there are two important features which can be read up. The first is all the secant elements are not fully fitted in this setup, but this feature can be supplemented, as I told you, by introducing one more vectorized family. And then, as the mixing with the vector-like singlets arise in the double currents, non-unitary of the secant mixing matrix can be naturally implemented. So we go to the next section. So here we discuss the scalar potential part. So this is the scalar potential we considered in this work, and then each scalar fields develops their pairs as described, and then. And the dimensional parameters can be related in terms of the scalar potential parameters. And since we are considering that all the scalars develop their paths, we consider that all these values must be negative, like as you can see here. So after diagonalization, CP even sector gives the three CP even scalars, and then this one is the lightest one, and then we consider this as the standard model Higgs, and then these two are the heavier the CP even scalars, and then in the CP order sector, after diagonalization, we get one Goldstone boson, which becomes the standard model Z gauge boson, whereas these two CP order scalars, as well as in the charge sector, the Goldstone boson for W gauge boson, and then the one charged Higgs. So all the new scalars can be parameterized in terms of the scalar potential parameters, and then from the CP even sector, the alignment limit conditions are implemented. Via the alignment limit conditions, we can recover the standard model Higgs from the extended scalar sector. So these alignment limit conditions are implemented between these three quantity coupling constants. So the lambda 1 ensures the standard model Higgs method, whereas the lambda 2 and lambda 8, these two ensures the alignment limit conditions. So here the constraints implemented are the mixing between the standard model Higgs and then the heavier CP even Higgs should be smaller than 0.2. This is experimentally checked. So if our mixing exceeds than this number, which means our model should be ruled out. So in order to avoid that, we put this first constraint, and then the mixing between the standard model Higgs and the heaviest the CP even scalar just vanishes. This is just a pre-parameter. So we banish these ones, and then mixing between the H2 and H3 is just a pre-parameter. So here this is our one of the main revisions compared to our previous work, because in the previous time we only have the three conditions, because generally we assume that the singlet flavor develops its pair and then consider the boundedness from below limits. But as we will discuss, this approach is not correct, because the order of each scalar is quite similar each other. So that kind of developing the singlet flavor pair and then applying finding this bounded from below limit conditions is not correct. So in this time, we consider all the scalar have the same orders. So in this way, we get to have the 3 or 4 more the conditions, which is more the correct. This is the correct result. So this is our first revision, and then this can be this bounded from below limits can be written like this way between all the conditions are expressed in terms of the quantity coupling constants, and then this is bounded from below limit conditions, and then we also checked the vacuum stability of the scalar potential using the high energy based tool, the pervasive. So For the vacuum stability, it can be determined as either stable or metastable state, in which the stable is when the electroweak symmetry breaking vacuum is a global minimum, which is what we want. And then also the scalar potential can be either metastable, which is a local minimum, but the tunneling time to a global minimum exceeds the age of the universe. So in this case, we cannot distinguish it. However, generally, what we found is metastable is very likely to cause some problems, because what we found is this scalar potential becomes metastable, but in this case, what we found is actually the width of the new physics scalar can be much higher than the experimental bounds. So which means metastable is very likely to be ruled out by experimental conditions. So for this reason, we collected only benchmark points whose vacuum state is identified as stable via pervasions. This is also the very important constraint. So now let's move to the flavor physics constraint. The first observable we consider is the muon anomalous magnetic moment. So this is our the second revision, because in our previous work, first of all, we checked this neutrino and the W constraints, like similar to this one, and then we confirmed that the effect is very negligible, and then consider that this is only the charged loops, which is quite misleading. But in this time, we consider both the diagrams at the equal footing. So in this muon G-master, the result, we get to have all the results together, not like one by one. So actually that is quite a misleading result, but in this time, we also corrected this picture as well. So the analytic expression for muon G-master reads like this way, and then all the loop functions are defined here, and then the experimental bound we consider is the 5.1 sigma discrepancy with this value. Next, we also consider the branching ratio of the tau to mu gamma to avoid its upper limit constraint. So this is the analytic expression. So the current experimental bound for tau to mu gamma is the upper limit is 4.2 times 10 to minus 8, as well as the tau to 3 mu, same order, and then also the CKM, the 0.04. So in our benchmark scenarios, we should avoid all these constraints. That is a very important condition as well. So now let's move to perturbative constraints. So here we first of all, in order to give you some sense of what bound we use, I prepared the effective operator. Here we consider an example to discuss an estimate of at which energy scale this theory can be trusted. So this is some kind of effective operator, and C is a Wilson coefficient, and the lambda is the cutoff energy scale. So here the C is the flavor violating the operator, so it is more convenient to define the C to be the C tilde, which is flavor conserving the Wilson coefficient with some mass terms. And one can now derive from these equations the rough estimate of the energy scale associated with the hypothetical MP contribute the new physics contributing to the muon G-master at different loop orders. So in three levels, this cutoff energy scale should be about 3,000 GeV, whereas if we consider this C is explained via one loop, then it should be 230, or the two loops, the cutoff scale become much lower than the other ones. So and so on. So assuming that it arises from an unspecified UV completion of our model of the scale, the cutoff scale lambda, it can be estimated by the corresponding the UV method M lambda and the UV Yukawa couplings, this one. So our muon G-master with this cutoff scale can be explained like this way, by demanding that the new contribution does not shift our phenomenological prediction for delta and mu by more than 3 sigma. We can derive a lower bound on the UV mass scales. So this is some Yukawa coupling constant at this cutoff scale, and then this 15 is derived from this constraint. Then we can estimate the cutoff scale of the M lambda. Then for the Yukawa coupling at the upper edge of perturbativity, so which is the square root of 4 pi. The equation 27 translates into a conservative estimate of the scale of the validity of our phenomenological model. So if we assume that our muon geometry is explained via one-loop contributions, then our theory must be valid up to the 50 TeVs by the LHC equations. This is a very important condition. So in order to give you a better sense, so I clarified what we discussed soon ago. So what the previous analysis tells is the following two pictures. First is for the perturbative conditions, Yukawa and Higgs coupling constant should be smaller than square root of 4 pi, whereas the quartic coupling constant should be smaller than 4 pi. All the coupling constant should be learning parameters. So here when you apply the LHC equation conditions, it shouldn't be applied to just the low parameter of the coupling constant, whereas it should be the coupling constant. So all these conditions, the smaller than square root of 4 pi or the 4 pi should be applied to the learning parameter, not just the pure parameters. So this is the first important condition. And then for the perturbative conditions with the learning parameters, the theory should be valid up to 50 TeV with respect to a lepton scale mu if your dominant contribution arises from one loop. Especially this is for the muon G mass, because in our model muon G mass is explained via one loop contributions. So in order for our muon G mass prediction to be valid, so our theory must survive up to 50 TeV. So this is our first benchmark points, the LHC running. So except for this lambda 1, lambda 6, and lambda 7, all the other Yukawas and the quartic coupling constants goes very slow, so very close to zero. So we don't express all of them, but most learning parameters, lambda 1, lambda 6, and lambda 7. And then by our LHC analysis, we confirm that our theory would be valid up to 1000 TeV. So this is the one. So the LHC running of the quartic coupling constant couplings lambda 1, 6, 7 for a random. So sorry, this is not randomly chosen, but this is our first benchmark points, and then which satisfies all the constraints. So the renormalization scale mu is ranges yes, the renormalization scale mu ranges from the 1.45 TeV to the 1000 TeV with respect to the reference scale 1.5 TeV, because here the heavy vector like quark method is about 1.5. So that's the reason why we set our reference scale as the 1.5 TeV in this zero. So the last check before leaving this section is a perturbative unitarity condition, which is required to be the smaller than 1/2. But this condition is likely to be automatically satisfied as long as the LHC perturbative conditions are met. So as long as our LHC runnings ensure that our theory is valid up to 50 TeV, then this condition is automatically satisfied. So we don't. But we cross-checked our benchmark scenarios, and then indeed our predictions is much lower than this value. So we could say our theory is valid. So here we discuss the numerical analysis and the benchmark scenarios. So this is our benchmark the input parameters. So tangent beta runs from 2 to 50, and all the quartic coupling constant and the relevant Yukawa. So the defined chi-square function is defined like this way, and the observer will consider this one. So all the second and the third standard model, the fermions, mu tau, the CS, and the PT, and the muon G mass. So, and then also we also wanted to be all the CK mixing matrix, at one sigma error bars. And then we want to avoid this tau mu gamma and the tau 3 mu and the theta CKM the upper bounds. So this is what we found. So actually, I'm sorry that this font is quite small, but you don't need to read everything. But here, what I want to say is that you can see we found 3 benchmark points. In which the tangent beta is ranged from nearly the 8 to the 13. So actually, we also try to find some other benchmark points in which tangent beta is the smaller or the higher. But very interestingly, we couldn't find any benchmark point in the region where the tangent beta is above than the 20 or the lower than the A. So actually this is very strong, looks like the strongly the fine-tuned, but this is actually the prediction of our theory, because our theory is very strongly constrained by the standard model parameters, the Yukawa sector, as well as all the scalar sector constraints like perturbativity and all the dimensional parameters, mu1 scale, mu2 scale, mu3 scale should be smaller than 0, and then as well as the vacuum stability condition and the bounded from below conditions. So actually, we also noticed that we also found that the benchmark, each benchmark is quite close to the other benchmark points. So this is our finding. And then also what we found is the order of our CKM anomaly is about this value, which gives the order of 10 to minus 4. So still this is very safe compared to the current the CKM, the upper limit. And then we also checked the breakdown of the chi-square functions. All the parameters are generally, all the chi-square contributions are less than 1, which means they are very well fitted. They meet the experimental values at within 1 sigma error bars. However, generally, most of our chi-square contribution comes from the CKM mixing matrix. So as I told you, we cannot fully fit all the CKM parts because this is the size much more sizable compared to other parameters. And then we also checked all the muon geometric contribution, and then we confirmed that the main contribution comes from this charged Higgs and the vector-like neutrino part. So this is the very nice picture because this is a nice picture because this is another main revision compared to our previous work. Because in our previous work, we only considered the charged neutral scalar and the charged the lepton contributions, which is quite misleading. So in order to fit the muon geometry at the time, we need to one of the quartic coupling constants need to be order of the 10, which is quite wrong. So but we didn't know that at that time by not considering the LG contributions. But in this time, we include in the analysis of LG contributions. So as you can see here, all the Yukawas and the quartic coupling constant are less than 1, which means they are very safe under LG constraints. So this is way more rigorously checked, and the cancer actually can survive from all the experimental constraints. So this result is here in our muon geometry prediction is not just a mere artifact of this benchmark scenarios, but a general feature of these models, which is very important progress. And then in this benchmark scenarios, we checked this new physics searches. First, we start from this vector-like quarks. So this vector-like quarks is carried out by the Atlas and the CMS as well. So we checked all the experimental constraints, and then this vector-like quark searches has been considered wrong, the model independent, but actually it's quite model dependent. That is what we found in this study. So first of all, let's look at this one. So in our benchmark scenarios, our uptype vector-like quark mass range is from this one. So and then this is our cross sections, which are given by the graph analysis. And then so before we discuss this experimental boundary on vector-like quarks, it is instructive to investigate how the signal is constrained. So let us look at the analytic expression for the pair production the process. So this total pair production process can be approximated by this narrow width approximations. And then Q is the vector-like quarks, uptype quarks or the downtype quarks, and then F is the standard model, the third generation T or P, and the P is the WG or the standard model Higgs. So the cross-section, we use the signal cross-section constrained by the experimental collaboration, this one. If under the assumption that all these branching ratios, their branching ratios summed up to 1. So here, if this becomes 1, then you can say actually this vector-like quark, the search channel becomes just the signal cross-sections like this one. But what we found is actually in the summing over this branching ratios doesn't sum to 1, but some smaller values, because the other new particles comes in this branching ratio, especially here you can see the maybe the up-type Higgs decay to the charged Higgs instead of W because their properties are similar, charged, but instead of W, you can consider the charged Higgs comes in this one. And since the other new physics comes in this branching ratio, what we found is this doesn't sum to exactly 1, but some much smaller numbers. So actually, this current the vector like up-type quarks and the down-type quarks, this bond gets much weaker because this branching ratio is much weaker. So let's say this summing over this branching ratio becomes 0.4. Then in this case, in this time, instead of 1, it becomes 0.4, and this term is repeated twice. So maybe you can see from this signal sections, maybe our real cross signal would be like weaker than 10 times. So in this way, what we found is our current predicted this mass ranges is slightly smaller than this current mass upper limits 1.6 and 1.4 TeV. If you multiply this actual branching ratios, actually it becomes 1.2 or 1.3 TeVs. So actually the vectorized quark search is not model independent, but actually model dependent. That is what we found. So by considering this summing over these branching ratios, actual our prediction becomes the one order lower compared to this just a signal cross section. So our prediction is all these three are safe, and then similarly we also checked the down-type quarks. So in this time, we also found that this W keeps way more significant compared to the others. Others quite suppressed, but the summing over all the branching ratios is quite similar to the up-type quarks. So if we sum up these three branching ratios, is quite similar to the summing over these three. So that is what we found because the picture is expected because U1 and the T1 they are mainly arise from the doublets. They are all mainly arise from doublets. So also for the down-type vector quarks, we found that the actual cross section gets weaker by the order of 1. We also checked not just the pair production but the single production here, and then in this single production its experimental bound is about 10 to minus 2 or 1, but the signal is weaker than the pair production. So we conclude the pair production constrain the parameter space more. So here the main findings in this vectorized quark searches are in our model, the single production is a less promising search strategy than the pair production. And then vectorized quark searches, which have been long considered model independent, are actually model dependent, especially the scalar sector is extended as our model is. Finally, in order to prove the vector-like quark method featured by our benchmark scenarios, at least one order of magnitude enhancement of the experimental sensitivity in the vector-like quark searches is required. That is what we found. And then we also checked the vector-like leptons, and so here in our prediction, the vector-like lepton, their masses range from 400 to 600, and then they are very compatible with the mass scale of the MP scalars. So here we put some the mass hierarchies between all the vector-like leptons and then the MP scalars. So in this arrow, we also checked the proton-proton to the vector-like leptons, all the vector-like lepton and the vector-like neutrinos. So their mass scales are ranged from like this way, or are quite similar to each other. And then the complete analytic expression for vector-like lepton decays can be written using the narrow width approximation as in the vector-like quarks. So in this time, like this way. And then we also checked all the dominant branching ratios over the vector-like leptons. And in this time, what we found is in all our scenarios, the vector-like lepton predominantly decay to the muons instead of taus. But the current vector-like lepton searches mainly focus on the third generation tau. So here we suggest that maybe it's good if the experimental group can focus on the final state with muon rather than tau, because their branching ratios are much more dominant. And then now with our current prediction with the third generation gives order of 10 to minus 6 or 7, which are five more the suppressed compared to the current experimental bounds. But maybe if the experimental groups focus on this muon instead of tau, then maybe they can enhance the suppressed prediction up to some more enhanced orders like 10 to 2 or 3, which are reachable in the current the experimental sensitivity. So that is what we also found, and maybe that would be very nice. That would be nice if they can check this the muon, the final state with muon, not the tau. Finally, we also checked the exotic scalars in the MP scalars, because our model features the type 2 Higgs doublet model as well as the singlet flavor, so we get to have more the MP scalars. And then the exclusion limit of PPH is first investigated via the Higgs tools. So in our study, we first of all checked the exclusion limit of our MP scalars via Higgs tools. So we collected PPs which only survive from the Higgs tools check. So all the benchmark, the 3 benchmark points survive from the Higgs tool exclusion limit check, and then we also carry out the cross check of the exclusion limit via med graph. And then what we found is this is the conventional tau channel, mu channel, and the BB channel, and this is also the charged Higgs channel. And then what we found is we checked all the CMS and at last the upper limits. This is experimental upper limit for the BP, the benchmark 1, 2, 3, and then this is our predictions. So actually, by comparing our prediction with the current experimental bounds, what we found is the tau channel is the most sensitive channels, even though our branching ratios are quite suppressed. So except for the tau, the mu and PB, they are less sensitive to the experimental bounds because they are slightly more suppressed than the tau channels. So here we also checked the dominant branching ratios of all the exotic the scalars, and then here I summarized the most important features in this exotic scalar searches. So the most important findings in the exotic scalar searches are the first is the most sensitive channel turns out to be the tau, even though the scalars, the branching ratio to tau are very suppressed. We confirm that it's less than the 1%. This is the most significant constraint. And then we also checked the other exotic scalar decay channels, including gamma, ZZ, WW, or this CP odd scalar A1 decay to the H standard model Higgs, and the are orders of 10 to minus 8 or 9 or below than that. So found that they are orders of magnitude below their current experimental bounds. Finally, the exotic scalar coupling constant to TT channel was investigated by the CMS collaboration, and then comparing the value of here they checked this new physics contribution to the TT via the coupling constant, not the cross section. And then what we found is we also evaluated this effective coupling constant via Espino, and then our prediction is 10 times lower than its current experimental bound. So confirming that no significant constraints arise in this search channel. So I will conclude our findings. In this study, we performed a global analysis of an extension of the standard model, which contains one full family of vector-like fermions and extra SGL scalar doublet and an SGL scalar singlet and muon prime global symmetry. First of all, we corrected many features which are bounded from below limit conditions for the full 3 scalar potential reversal. And then next, we also considered the LG equations, which wasn't considered in our previous study. So And then the muon G minus 2 explained by contributions consisting of charged leptons and the neutral scalars only in the previous work, leading to a totally misleading result. Plus the other constraints such as vacuum stability and MP scalar. But in this work, we counted all the contributions. So the charged lepton as well as the neutrino contributions. So all the parts of the contributions. So this is the way more rigorously checked, and then by also the considering the vacuum stability and the MP scalar limits are more rigorously checked in this time. So as I told you, this in this work, our muon G minus prediction is not just a mere artifact of benchmark scenarios, but the general feature of these extensions. All the numerical predictions are generated by Espino for reproducibility. In this time, we avoid generating our prediction via handwritten code, but using this Espino code to for reproducibility. And then we found that none of the currently available exclusion bounds can test the spectra featured by the benchmark scenarios. So it would be nice if our prediction can be confirmed via some currently learning the experimental groups. So the cross sections for the pair production of vector-like quarks featured by the benchmark scenarios are one order of magnitude smaller than the current experimental upper bounds. And then both the charge and the neutral vector-like leptons decay predominantly to muons in our framework, thus confirming the need of dedicated analysis of the vector-like leptons coupled to the second family of the standard fermions, not the third family tau. Finally, we observed that the most constraining decay channel for exotic scalars is the tau-tau channels. However, the ultimate verification of the MP scenarios considered in this study may come from the flavor physics. Sorry, I forgot to say that, but actually, we also noticed that while fitting the muon G minus, the most strongly correlated channel is tau to mu gamma. They are very close to the 90% exclusion limit. And then next, we consider the collider channel, proton-proton to the vector-like quarks, and then the tau-tau channel. So we confirmed these three channels are most significant ones, especially tau to mu gamma. So if you are curious about the details of this work, I recommend you to refer to our paper in this archive number. So, okay, thank you very much for your attention. And if you have any question, please feel free to ask me. Thank you very much.
Thank you very much, Huchan, for the very complete, nice and complete talk. Question from the audience? Any questions? Huchan, did you consider extending this model by adding, for example, an extra scalar doublet to have ladditive mechanism for neutrinos?
Antonio, sorry, what do you mean? We extended this model via the down-type doublet Higgs.
Yes, because in principle it could be extended. For example, you could have ladditive mechanism for neutrinos, because you had three-level universal solve for everything. But in principle, you could extend the model to have, for example, an extra scalar doublet apart from HU and HD, and let's call it HD prime. And you may have, for example, preserve EC2 and neutrino masses radiatively.
Antonio, you mean the inner scalar doublet model or something like that?
For example, it will not be inner, it will be 2 + 1, for example. 2 active Higgs plus 1 inner Higgs, for example.
Yeah, I think that's the good picture, but the problem is that let's say if we include one more doublet scalars, then maybe the scalar potential would be way more complicated, and maybe it would be quite challenging to check, because here we very rigorously checked all the scalar potential constants via the Obeyus and the Higgs tools. So maybe I think that can be done in some more simplified model, especially focusing on the neutrino sector mainly. But in this time, we didn't consider. But I think that could be a nice work in the future.
Yes, the scalar sector will be a bit more complicated. I mean, the part regarding the stability condition.
Yes,
On the other hand, the scalar mass matrix, yes, will be large, but if you have ladditive mechanism, you will have an extra this model could be extended by an extra discrete symmetry, preserved
Yes.
discrete symmetry. So the extra scalar field will not have mixing with the active scalar field. So in
Yes,
that way,
indeed, I'm looking at the inner doublet model. So maybe I think yes, maybe if there is a chance we can work on that. But actually, indeed I'm looking at the inner doublet model. So and then but in this work we consider all the doublets which has the therapies. Maybe.
there could be an
Maybe,
extended work, could be a continuation, for example, with
yeah.
I mean, this scalar content plus an inner doublet. And this inner doublet, when one performs the analysis of the scalar sector, when you analyze the scalar sector, there will not be missing between the component of the inner doublet and the component of this scalar doublet. So the part regarding the active scalar sector will remain the same as in this paper. The extra new ingredient will be the scalar mass for the inner doublet.
Yes, I think
What
so.
will be a bit more complicated will be stability on conditions of the quartic coupling from below. This there will be an extra condition on the quartic coupling because you will have extra quartic coupling.
Yes, I think so.
More questions from the audience? If there are no more questions, we send Huchan Lee for the very complete talk, very comprehensive talk, and we meet at the next seminar. Thank you very much, Huchan.
Thank you, Antonio.
Thank you.
Bye.
Thank you. Bye-bye.
Bye.
Bye.